All right, we're going to finish up the notes from the last time we met and go over a couple more things on top of that here. So we left off on this problem where I asked you to do a midpoint Riemann sum, and some people were having some trouble with it. So first off, midpoint sum with 3 subintervals, okay? So if you want 3 subintervals from 10 to 70, right, that means that we're not worried about the 0 and the 80. We're only worried about from 10 to 70. All right, so if I want to split the interval from 10 to 70 into 3 pieces, well, the 3 pieces would be to go from 10 to 30, 30 to 50, and 50 to 70, right? That would be our 3 subintervals, okay? 10 to 30, 30 to 50, and 50 to 70, 3 subintervals. And then, since we want the midpoint sum, we're going to take the midpoint of each of those intervals. So, for example, for the 10 to 30, we want the midpoint of 10 to 30, which is 20, right? And so this is what the diagram will look like, all right? And that'll determine what y value we use. Okay, so we're going to use the y value of 20, the y value at 40, midpoint between 30 and 50, and the y value at the midpoint between 50 and 70, which is 60. Okay, so this is what the midpoint sum looks like. All right. So remember, each of these rectangles, area is going to be base times height. So our base of each of these is going to be 20, right? From 10 to 30, that's going to be 20. And then the height is determined by our y value, okay? So 20 times, well, this is v, so 20 times v of 20, plus 20 times value at 40, plus 20 times value at 60, right? The midpoints of each of the subintervals. All right, plug those values in. This is straight off at the table. If we plug in 20, we get out 22. These are the values that the table gives us. Plug in 40, we get 35. And since all of the intervals are of equal length, the bases are all 20, we can factor 20 out. And when we do that math out, we get 2,020 feet. Feet should hopefully make sense here, because when we're multiplying base times height, right, base is 10 to 30, right, we get that from time. So we're taking feet per second, or we're taking seconds and multiplying it by the velocity in feet per second. So we're taking seconds, multiplying it by feet per second, and that should get us feet. Okay? So take the midpoint of each of the intervals. This is where drawing a picture is really going to help you in doing these. All right, that's number 1. Next one. And before I show you the answer, I'll give you a minute to try and draw out this picture. Remember, right Riemann sum. So you're using the right endpoint when you draw all these rectangles. Okay, here's your diagram. Okay, and hopefully you notice, before I even show more, hopefully you notice that these are not all of equal length this time, right? They're not all 20, so we're not going to be able to just take a 20 out like we did last time. Right, some of them are narrower and some of them are wider. So the base here for the first rectangle, for example, is from 0 to 2. So our base is 2. And then our height is determined by the right endpoint. So since we're drawing the rectangle from 0 to 2, we want to use the rightmost of that, so we're going to use the y value at 2. And then from 2 to 5, our base is going to be 3, right? That distance from 2 to 5. And then our height is going to be the y value at that right endpoint of 5. So 2.0. Okay, and so on. And this is kind of a general case. If you're doing a right Riemann sum, then you're going to use everything except the left endpoint, right? So we don't use the value at 0 because this is a left endpoint. This is our leftmost value. So we're not going to use it in a right Riemann sum because we're using all the right endpoints. And it's going to be the opposite for a left Riemann sum. If you were doing a left Riemann sum, you wouldn't use the left, or if you're doing a left Riemann sum, you wouldn't use the rightmost endpoint. You wouldn't use 12. All right, but again, all different base lengths determined by our distances and the x values. Then multiply that out. All right, this again, straight from the table. R prime of 2 is 4. R prime of 5 is 2. And so on. So add those together. This is about as complicated as a non-calculator question will ask you to do as far as calculations go. Because they're less interested in can you multiply and add all these decimals together, and more interested in, do you understand the calculus of making the rectangles and writing out what the sum would be. So this addition is probably about as complicated as a non-calculator question would get. Any more than this, and they'll give you the calculator for it. Okay. And again, 5 different rectangles. And there's your sum. And once again, feet, because in each of these we multiply feet per minute by minutes. So the second part asks us to interpret this. I'm going to leave that kind of open for now, but you should be thinking about, since our units are feet, it should be something about the radius itself, right? It should be something about the length, and probably something about what the length does between 0 minutes and 12 minutes, right? Because we're going from 0 to 12. All right. But one other idea I want to talk about is approximations, because a lot of times, or even on your homework, they like to ask about over approximation or under approximation. And the way you can determine that is by increasing or decreasing. Right, so here's another example of a right Riemann sum. Right, this time it's concave down as opposed to this one, which is decreasing and concave up. So anytime we're decreasing, the right Riemann sum is going to underestimate. And that should make sense if you think about it, right? Because if we're taking the right endpoint, if the function's decreasing, if it's getting smaller and smaller, then the values on the right are going to be always going to be smaller than the values on the left. Right? So if we're using the right endpoint, we're using the smaller value, and we're always going to be smaller than the actual area. So this is going to underestimate the actual area underneath the curve. Okay? And it's going to be the opposite for left Riemann sums. So for right Riemann sums, if we're decreasing, we're underestimating, and increasing, we're going to overestimate. Again, because right endpoint is always going to be higher in an increasing function. So the rectangles are going to come up higher than the curve does. And you can draw these pictures yourself and draw out the rectangles and verify this. But yes, it's determined by increasing and decreasing. That would be your reasoning if it asked you to explain why something over or underestimates. And another common question is about tangent lines, but we'll talk about that later on, whether a tangent line is going to over or under approximate. That's another one that I might leave open to you to think about. If I'm approximating from a tangent line, is that going to over or underestimate the actual value a little bit to the left or a little bit to the right? Okay. But let's get a little bit more of a grounding of what we're doing and what this notation says. Okay? So to find the area under the curve, first of all, this is where the sigma notation comes in, the summation notation that we were doing, is that imagine we have this approximation. Hopefully you see that if we make more rectangles, so let's say we used, instead of using 3 rectangles, maybe we split this into 6. We do 6 different rectangles, from 10 to 20, from 20 to 30, and so on. That would come closer to our actual answer than 3 rectangles does. And then let's say we did 60 rectangles, right, of a base of 1 apiece. So from 10 to 11, 11 to 12, all the way up to 70. We need 60 different rectangles. That would be an even closer area. So let's let the number of rectangles go to infinity. In other words, a limit as the number of rectangles approaches infinity of this sum, right? That's the more technical way that we write out our integrals, and we'll talk about that more when we come back. But that's what we're doing, and this is called an integral. This is called a definite integral. And definite because it has these bounds, and it's going to give an actual number as our answer. We're going to get a number out as our answer, versus an indefinite integral where we're going to have a more general answer. But this is a definite integral. All right, so this is our integration symbol. And then this a and b are called our bounds of integration. Right, so this is saying we start at a, and then we measure up to b, and we're finding the area between the curve and the x-axis. Right, so this is an integral from 0 to 12 because we're starting at 0 and we're going up to 12. If we wrote out this integral, it would go from 10 to 70. Right, so those are our bounds of integration. Those are our bounds of integration. And then this part, the actual function, this is called the integrand. This is called the integrand. Just like underneath the radical, which is our square root symbol, the thing underneath the radical is called the radicand. So the thing inside an integral is called an integrand. And usually it's just going to be our function, f of x. Right? To say that we're finding the area underneath the curve of this function. From a to b. From our bounds of integration. Okay, so that's kind of our terminology that we're using. Now let's look at some properties. And this is on the very back, this part is on the very back page of your notes. So, property number 1. If f is defined at x equals a, then the integral from a to a of f of x dx equals 0. Okay. And I'll give you a couple seconds to pause and think about, in terms of area, why this makes sense, that this should come out to be 0. All right, and hopefully you can come back and realize that if I start at A and then end in that same place, then there's no real area to find, right? If I take a function like up here and go from 10 to 10, then there's not really an area to find. And so that we say that that area is just going to be 0. So if the lower bound and upper bound are the same, then we don't have an area to find, and we say that the integral of that is 0. Okay, doesn't matter what the function in here is. Okay. Then, here's a couple more properties. All right, this is if we switch the bounds here, right? Before we have b to a, and now we have a to b. All right, so if we this is a kind of a way of measurement. So if instead of reading from left to right, we start reading from right to left, then it becomes the opposite of that area. So if I start at B and end at A, then that is going to, our rule is going to be that we're going to make that negative. That's a negative integral from A to B. And we'll see algebraically why that is. But if we're measuring backwards, then we're going to make that answer negative. Okay. Property number 3. Property number 3 is saying that if we put some c in the middle, right? If we put some c value in the middle, we can actually split this up into 2 different areas, right? So let's say I have some c value that's somewhere in between a and b. Then what this is saying is that we can say that the entire integral, we could start from a to c, measure up to there, and then measure from c to b, and then add those two pieces together to get the entire area. So we can basically split it up into two different integrals and find them separately, and then add them together to find that total area, right? And sometimes this is going to be an easier technique than trying to find it all at once. Or if we know the whole area and then only know part of it, then we could subtract that one of the pieces from the whole to find what the other piece is going to be, right? That's going to be our two different uses for it. But it's basically splitting the area up into two smaller areas. It's saying that that's allowed. Next one, if we have two different functions, we can add and subtract different integrals together. We can split them up. Again, sometimes it might be easier to find the integral that way is by splitting it up into two different ones and to take it one function at a time. And if there's a constant, then we can move the constant out in front, right? We can move the constant out in front. And we're going to do this pretty often just to make our numbers smaller and easier to work with. Okay. All right. So we're going to use these properties in this example here, using the following values. So we got these three different integrals. Now, first of all, there's some of these that you should be able to know without any calculus. For example, integral from 1 to 3 of dx. All right, what is this function? Well, the function, what can we multiply by dx to have it be the same value? Well, 1. So really, this function is just y equals 1. All right, and if I take y equals 1 from 1 to 3, and I would encourage you to draw a picture of this so you can follow along. If I have from y equals 1 from 1 to 3, then all that is just a rectangle, right? Because we got a horizontal line that we're cutting off at 1 to 3. And so we have this rectangle that we know the area is base times height. And the base from 1 to 3 is going to be 2. And then the height is going to be 1, because it's at y equals 1. And so 2 times 1 is going to be 2, all right? And you can do that for this function too. Because if you drew a picture of this, this would just be a trapezoid. And you could find that the area of that trapezoid would have to be 4. All right. But we're going to use these properties to get this more complicated integral of this downward facing parabola. And again, you should be able to draw a picture of this pretty quickly. The zeros are at 1 and 3. And it's a downwards facing parabola. So we're finding the area between this and the x-axis, right? That's what we're doing when we're finding integrals. Okay. So we're going to use this to get this integral. And the first thing we're going to do is we're going to split this up into 3 different integrals. Okay. So that's our first step. So integral from 1 to 3 of negative x squared, and then plus the integral 4x plus the integral of negative 3. All right. So splitting it up into 3 separate integrals, since we don't know how to do this with the more advanced methods that we're going to learn later on. Right? We're going to take this in a different way and get the same answer later on. But for now, we're just going to use our properties. All right? And then our next step we're going to use is that we're going to take all the coefficients and put them out in front. Okay, so the coefficient here is negative 1. So we can put a negative out in front of here. And then our coefficient here is 4. We can put it out in front of here. And then our coefficient here is a negative 3. We're going to take it out in front. And then we have it in terms of our 3 different integrals that we know. So we have, for example, 4 times the integral from 1 to 3 of x dx. Well, we know this is 4. So we can just make this 4 times 4 and substitute in for all of these. And when we do that, we get negative 26 thirds plus 4 times 4 minus 3 times 2. So this is 16 minus 6 is 10. So 10 is 30 thirds. So 30 thirds minus 26 thirds, 4 thirds. All right. And again, we'll have an easier way to do this later on where we'll see that the answer is still 4 thirds. But for now, that's kind of demonstrating our properties of integrals. Homework. So there's a new book assignment for you. I may also give you something to do with the online textbook, and I'll have that information for you later on. But this is your homework assignment. Most of these problems, these three are going to be using the properties of integrals that we just looked at. Most of these problems are going to be using area in order to get our value of the integral. Because I really want you to be able to connect this idea that integral is going to be area under a curve. Okay, so let's look at an example out of this assignment, actually, just to get you started with what you're going to be doing. So you're going to draw the picture, and you should come up with some pretty easy geometric figure to find the area of. All right, so this is problem number 17 out of this assignment. We've got the integral from -2 to 1 of absolute value of x dx. Okay, so the first thing you're going to do is draw that picture. So pause and do that. And then you want to section off the area from -2 to 1. So it should look like this. Right, there's your absolute value graph. And then we want from -2 to +1. That's our area that we want. Okay. And so these are just two different triangles. We can just section off this area, and area of the triangle is 1/2 base times height. And we can section this off because we got a property that says this. We can split this into two different integrals. Integral from -2 to 0 and the integral from 0 to 1, which is what we're going to do. Because we got two different triangles, we can just take those two triangles' areas and add them together. So this one, the base is 2, and the height is 2, because that's the y value at -2. Absolute value -2 is +2. So we got 1/2 base times height. So this ends up being half of 4 is 2, plus half of 1 is 1/2. So 2.5 is going to be 5/2. So the steps in these problems are going to be draw the picture. It should be some pretty simple geometric figure. So you're probably going to be working with some triangles, some rectangles, maybe some circles, trapezoids, those kind of things. And you want to use what you know about area in geometry to find those integrals.